Hello, in today's video we are going to be talking about the behavior of waves, and basically what we're going to be looking at is how waves interact at boundaries. So let's get right into it. So a boundary basically can either be one of two things. It can be a wall and what happens when that wave hits that wall, or it can be that a wave is transmitted from, say, a thin rope to a thick rope, or from like air to water, or something like that, a new medium it enters into. So when a wave is traveling through that new medium or hits an obstacle, what happens? Does the frequency or wavelength change? Does the amplitude change? Is the wave even reflected in the first place? And those are all questions we're going to try to answer today with various scenarios that I will present to you. So let's take a look at the first scenario. This is called wave reflection. All right, and wave reflection basically means that you put a pulse through, in this case, a rope. So here I've got my hand on a rope, and if I put a pulse through it, this rope is actually attached to a pole and it's fixed there. It can't move up or down. It's stuck at that point. And I put a pulse through a rope, and that pulse is called an incidence pulse, or an incident pulse. And basically it's the pulse that's traveling towards the new, or towards the pole, I should say, in this case. The wave that reflects back is appropriately named the reflected pulse. And here you can see here's the incident pulse traveling towards the pole, and then it hits the pole and it reverses direction in terms of a reflected pulse. What you need to know is that when a wave hits this barrier, the reflected pulse will have an inverted amplitude, meaning it flips. Okay, so this way it's up, and on this side it's down. Okay, and that's inverted amplitude. And this happens anytime a rope or whatever is attached to something that's fixed, that's not able to move. What happens if this is able to move? What if this rope is able to go up and down? Well, that's what the next slide's about. Oh, I lied. We're going to talk a little bit more about some of the fixed wave properties. Basically, a few other things that you should know is that for a fixed wave, the frequency and wavelength are going to stay the same. There is no change. Even though the amplitude's inverted, the frequency and wavelength stays the same. The speed of the wave also stays the same. The only other change is the amplitude is a little bit smaller than the incident pulse. So I mean, if I draw a incident pulse traveling to a pole, if it hits this pole and then it starts to reflect back, remember it's going to be inverted, the amplitude will be a little bit less than this one up here. Okay. All right, so the next type of reflection is called free end reflection. And in the previous example, this rope was attached to this pole. It couldn't move. Well, now this thing is able to move. It's free to move up and down. What ends up happening? Basically, everything's the same, except the only difference is the reflected pulse's amplitude is not inverted. Okay, but all the other things I just mentioned stay true. The speed stays the same, the frequency stays the same, the wavelength stays the same, and you'll notice here too, the amplitude is a little bit smaller on the reflected pulse compared to the incident pulse. Okay, so that's basically what happens with a wave on a rope if it hits a pole or a wall or whatever the case may be. What happens when a wave, say in a rope again, is traveling through a rope and the rope is thin at the one end, and you hit a point and it gets a lot thicker. So I'm going to make a thick rope here. It gets thicker. So you're going to send a wave going this direction through this thin rope, and then it hits this thick rope. What happens? If the wave travels from a thin rope to a thick rope, what ends up occurring is the incident wave hits the thick rope. Okay, so this incident wave that's traveling along hits this thick rope, and it's reflected and inverted. Okay, so if let's say I have another, like, I don't know, 10 seconds later, we have a wave now that's inverted, and this is the reflected wave. Okay. So one thing that happens is that the wave is reflected and inverted, and the second thing is part of this incident wave, which is represented over here, part of this incident wave is going to be transmitted into this thick rope, and that's called a transmitted pulse. Okay, so part of it goes into this thick rope, traveling again still this direction. A few other things to keep in mind when we're still dealing with thin to thick ropes is the transmitted pulse travels slower than the reflected pulse. Okay, so this transmitted pulse in the thick rope is going to travel slower than that reflected pulse in the thin rope. The transmitted pulse has a smaller wavelength than the reflected pulse in the thin rope. And again, this does get a little bit tricky because we keep talking about different ropes and stuff, but try your best to just get your notes organized that you have these properties that are going to happen. The speed and the wavelength of the reflected pulses are the same as the incident pulse. So remember, the incident pulse is the original one that's on the thin rope, and it's going, say, this direction. When it reflects, and there's a thicker rope here, when it reflects, it is going to be inverted, and the wavelength of the reflected pulse is the same as this. So the wavelengths will be the same. Okay, what happens if we flip it around and we're going from, say, a thick rope to a thin rope? Okay? The incident wave, which is right here in this picture, in the thick rope hits the thin rope, and the reflected wave now is not inverted. Okay, you'll notice the reflected wave is still in the same direction as the incident pulse. And then you still will get a transmitted pulse. Okay, some of it still transfers into the less dense area. So no inversion occurs. A few more things about thick to thin ropes. The transmitted pulse in the thin rope is traveling faster than the reflected pulse in the thick rope. And this kind of makes sense. If you remember, wave speed is dependent upon the medium in which it travels through. So a thin rope is going to let the wave travel faster than, say, a thick rope would. The transmitted pulse also, which is known as what's in the thin rope, has a larger wavelength than the reflected pulse, which is in the thick rope. The speed and wavelength of reflected pulse are the same as the incident pulse. Okay, so again, I know it's a little confusing, but I think this conclusion slide right here will kind of clear things up. So in a nutshell, what is this lesson about? The wave speed will always be the greatest in the least dense rope. Okay, and density of rope really is referring to thickness. So a thin rope is going to be fast. A thick rope is going to be slower, the wave speed. The wavelength is always greatest in the least dense rope. So if we kind of have like a chart here, it's going to be fast in terms of speed. The wavelength is greatest, okay? And over in this thick one, it'll be slow, and it'll have a smaller wavelength. The frequency of the wave is not altered by crossing a boundary, which is kind of interesting. I wouldn't think that would be the case, but it actually is. The frequency of a wave isn't altered by crossing these boundaries. The reflected pulse becomes inverted when a wave is in a less dense rope is heading towards a more dense rope. So if you go from less dense to more dense, the reflected wave becomes inverted. If it's more dense to less dense, there is no inversion. And the amplitude of the incident pulse is always going to be greater than the amplitude of the reflected pulse. All right. Now this might be one of those videos that you might need to watch more than once, just because I went through a lot of this really fast, and there really aren't tons of examples I'm going to do in the video. We'll practice more in class, but you may need to go through this one more time just to kind of wrap your mind around what was just said. All right. So that takes care of this video. We will see you guys next time.